Hello, class. In today's video, as the title suggests, we're going to be talking about change. And so we're going to imagine that in this world we have just the coins here. So we have pennies, we have nickels, we have dimes, and we have quarters. And the question we're going to have in mind is, how many ways are there to make change for a certain amount? So in this case, this would be one way to make change for 58 cents. Okay, but I'm going to ask in general, if C of n, for n some positive integer, this is going to be the number of ways to make change for n cents. Okay, and so just like last time, we're sort of going to follow along with an example so we can make sure we believe the thing I'm going to write down. And so this is one way of doing it for 58 cents, which is 8 pennies, 1 nickel, 2 dimes, and a quarter. But the thing I really want to know is I want to know not just the answer for one particular number, such as 58. I actually really want to know what is the generating function of this thing. So if I take the sum as n goes from 1 to infinity, or even really 0 to infinity if I want to be super careful, of c of n times x to the n. Okay, and so I want to figure out what this function is in some coherent way. Okay, so the thing I'm going to need here, just like in our example with the dice before, is I'm going to need some basically product where each term in the product corresponds to one of these types of coins. So I'm going to need something that tells me how many pennies I have, something that tells me how many nickels I have, something that tells me how many dimes I have, and something that tells me how many quarters I have. Okay. So let's start with the penny one. So the way I'm going to talk about the amount of pennies I have is I'm going to write down this polynomial. 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth plus x to the sixth plus x to the seventh plus x to the eighth. And I can think about, when am I going to stop? Well, actually, if I'm just talking about an arbitrary n, I have no idea. I can't actually stop. So when I called this a polynomial, I actually lied slightly. This is actually itself a power series. And so the number here, the power of x, that's telling me how many pennies I happen to have chosen. So in this case, I happen to have chosen 8 pennies. Okay, so for this particular distribution, I'm going to zoom in on that. Okay. Next up, I want to think about nickels. And it might at first be our inclination to say, okay, I'm going to have 1 plus x squared, because I could have 1, 2, 3, 4, 5. I could have however many nickels I want. But nickels don't count for 1 cent. So if I have 1 nickel, I want the 1 nickel to carry the weight of a nickel, which is 5 cents. So that means I want to jump straight from, okay, I've got no nickels, to, okay, 1 nickel would bring me all the way to x to the fifth. Okay. 2 nickels, that would get me an x to the 10th, plus an x to the 15th, plus, and so on like that. Okay. Here I have 1 nickel, so I should think of this as having 5 cents worth of nickels. That's what this x to the fifth is telling me. And so if I put together, just so far, the term corresponding to how many pennies I have, which was 8, or 8 cents of pennies, if you prefer, and 5 cents of nickels, or 1 nickel, that tells me so far I've got 13 cents of coins. Sounds good. Okay. When we go to talk about dimes, we can figure out what's going to happen. Namely, we're going to say, okay, I could have no dimes, in which case I have x to the 0th cents, or I have x to the 0th as my term, which would say I have 0 cents of dimes. Or as soon as I have 1 dime, I have 10 cents of dimes, or 20 cents of dimes, or 30 cents of dimes, or whatever, and so on. Okay, and so there we go, like that. And then last up, we have to deal with quarters. Oh, sorry, I should say we had 2 dimes. Okay, and so last up, we have to deal with quarters. Sorry, that way. And so again, as soon as I have 1 quarter, I've got 25 cents in quarters, or I could have 50 cents in quarters, or whatever. Okay, and so we've got that. And so 1 quarter, that corresponds to this, 25 cents in quarters. Okay. So I want to know a nicer way to write this, because this is technically true. If you multiplied all of this out, you would get this function c of x. But that's a little bit messy. So what I actually want to do is I want to realize that actually all 4 of these lines, these are all geometric series. Namely, this is a geometric series with common ratio x. This is a geometric series with common ratio x to the 5th, one with common ratio x to the 10th, and one with common ratio x to the 25th. So this, if I keep writing it, will end up being equal to, okay, and so remember the sum of a geometric series. So the sum of, so this is just a formula. So the sum of 1 plus x squared plus dot dot dot. As we did in the last video, that's 1 over 1 minus x. So this is 1 over 1 minus x times, and then the second one here, sorry, let me pull that down just a smidge. The second one here, now the common ratio is x to the 5th, so I need to put an x to the 5th in for x in this first line. So that'll be 1 over 1 minus x to the 5th. Okay, and then this one has x to the 10ths times, and then 1 over 1 minus x to the 25th. And so this function c of x, the generating function for the answer to this change-making question, is in fact fairly concisely written as 1 over 1 minus x times 1 minus x to the 5th times 1 minus x to the 10th times 1 minus x to the 25th. Okay. Now, as we sort of go on, we're going to end up using this sort of idea a lot, where we're going to talk about the number of ways to put together things or put together numbers with a certain constraint, where the idea is we want to add up to some total. And so if you were to expand, grab Sage or Wolfram Alpha or whatever, the Taylor series of this function, and you were to go to the x to the 58th term, the x to the 58th term here would tell you how many ways there are to write this particular, or how many ways there are to make change for 58 cents with pennies, nickels, dimes, and quarters. Hello, brief interlude. This is Tommy from the future. So I mentioned that we could go ahead and calculate the Taylor series of this thing, and then that would tell us the answer to this question for anything we want. So I went ahead and did that, and if you do that, you get this thing. So This, by the way, is Wolfram Alpha's way of saying that these are the first 97 terms of this, and then if you want more, you have to ask Wolfram Alpha nicely. But in particular, if you wanted to know the answer to our original question, how many ways are there to make change for 58 cents using these 4 coins, then you could look up to the 58th term here, and you would see that there are 60 ways to make change for that, for 58 cents. And if you wanted to go up to, say, 97 cents, then there's 213. And if you wanted to figure out how many ways there are to make change for $1, then you'd have to ask Wolfram Alpha to calculate more terms, or more likely, perhaps, end up switching to Sage for that. All right, I'm going to hand things back to future Tommy, or sorry, back to past Tommy. I am future Tommy. I'm going to hand things back to past Tommy to finish up this video, but I wanted to show you that. Okay. So, I want to do a question that we did a few videos ago again. Namely, a few videos ago, we talked about this question. Namely, we talked about what is 1 over 1 minus x squared? What is the power series of this? Or what does the generating function of this look like? Or et cetera, et cetera. And the way we did that at the time was to notice that this is actually the derivative of 1 over 1 minus x. And so we wrote out this, and then we just took the derivative and said, okay, well, it's going to be 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus blah, 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 blah. Which is fine. You can do that. But what we can actually do is we can actually reverse engineer this. And instead of doing it this way, we can say, okay, well, what is this? Well, this is literally 1 over 1 minus x times 1 over 1 minus x, which is 1 plus x squared plus dot, 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 times 1 plus x squared plus dot, dot, dot. And so if I were to write this as a sum, where I've got an x to the n here, and going from 0 to infinity, what am I counting? So I can now really, if you want to think about it this way, what I'm doing, I can do this calculus question as a combinatorics question, because I'm really asking how many ways are there to get an x to the n out of this, which is really saying how many ways are there to choose 2 non-negative integers, that is a power of x here and a power of x here, that give me an x to the n. Okay, and so imagine, for example, that n is 8. How many ways are there to choose something on the left and something on the right that'll give me out an x to the 8th? Well, I could pick 4 and 4, or 3 and 5, or 2 and 6, or whatever. And ultimately, if you think very carefully about this, you'll figure out that the answer is n plus 1. Really, if you want, you can say, I'm going to count, okay, if I choose 1 in this, I can pick x to the 8th over here. If I choose x here, choose x to the 7th over there, all the way up to if I choose x to the 8th here, I can choose 1 there, and then I'm done. If I choose x to the 10th here, there's nothing I could put over here that would get me an x to the 8th. Okay. And so it's n plus 1 because you started at 0 and then went all the way up to n. Okay. Before we wrap up this video, I want to go ahead and generalize the thing we just did. Namely, I want to think about what happens if you take 1 over 1 minus x to the kth power. So that is going to be 1 over 1 minus x times dot, 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 times 1 over 1 minus x, which is going to be 1 plus x squared plus dot, 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 plus x squared plus dot, dot, dot. Okay, so that's going to be that whole thing. Okay? And I again want to imagine that what we're doing here is we're going to recollect all of this as something times x to the n for each n. And so we've got to figure out what goes here. So I'm asking how many ways are there to choose a power of x from each of these terms to multiply together to be x to the n. So really, the thing that goes in this blank is really the answer to the question, how many ways can we choose k non-negative powers of x to multiply to be n. Okay, or really, what this is saying is if I say the one I choose from the first is k1, and then the one I choose from the second is k2, this is really saying how many ways are there. Oh, k was a terrible letter to choose. Sorry, instead of k, we're going to make these r's because I can turn k's into r's. If I choose the r1th power here, the r2th power from the second, all the way up to the r-kth power from the third, I need that sum to be n. Okay. But this is a now familiar question, because now I'm saying how can I choose k non-negative integers that add to n? Or if you want, all I've really done here is written a very calculus-y way of asking the kid and candy bar question. So I could say here instead, I'm asking the same question as if I was asking, if I want to give n candy bars to k children, how many ways are there for me to do that? And so R1's the number of candy bars I give to the first child, then the second child, all the way up to the kth child. And so we know the answer to that question. Namely, this is that whole stars and bars business. So I have to write down this thing where I've got the n candy bars and then k minus 1 dividers. And then I'll go ahead and choose where the k minus 1 dividers go. And so, in fact, actually, if you were to write out the Taylor series of this function, this sort of natural-looking function that you've assuredly thought about before in calculus, then its coefficients correspond exactly to this kid candy bar question that we've been talking about on and off for the whole semester. All right. I'm going to wrap up there. But next time, we're going to talk about a different question that we've talked about a bunch of times that's related to all of these sorts of things. So namely, we're going to slowly get towards talking about how we can frame this kind of discussion to talk about partitions. Until next time, though, be well.